So when we create a simple variable like this, what the computer does is that it creates a key value pair, a dictionary behind the scenes. So imagine we have a dictionary where the key is x and the value is the variable's value. So in this case, it's 5. And obviously this 5 is stored somewhere in memory. Let's say this is our memory. This is memory, and this is the first slot. So 0x0, 0x1, and so on. This x is placed somewhere in memory. Exact locations do not matter for us as developers. So, and when we want to read the value, let's say we want to print it like this. What the compiler does is that it basically sees x, and then it checks this dictionary, and it sees the value 5, and then it swaps it here for 5. Obviously, this is an specification. And if you want to create a new variable, let's make it a. It does the exact same thing. It calls a and then writes 10. So a pointer is also just a number. In the hardware level, there is no difference between a normal integer and a pointer. What changes is that how the compiler treats. When we create a variable and we say that it is a pointer, the compiler stops treating the value as just any number, but it starts treating as a memory address in the computer's RAM. To create a variable, you can simply put the star sign after the variable type. You can also do it like this. Skip it like that. So now, since this is not a normal variable, we cannot just assign it any value we want. We need to assign it a memory address. To do that, let's create a new variable. Let's call y, and then since this is a normal variable, we can just assign a value to it. And then we can assign the memory address of y to x. To do that, we can simply say x equals n% y. This n% symbol means the memory address of this variable y. So what happens is that there is a dictionary of x, which is a number that hasn't been declared yet, and of y, which with the value 814. And in the computer RAM, these are all stored somewhere. So let's say the value of y is stored on 0x15. When we say n% y, instead of saying 814, we mean the memory address it is stored in, which in this case it is 0x15. So saying x equals n% y is actually assigning the memory address to y. So x, my bad, to x. So x becomes 0x15. And if we just try to print it normally, like a normal variable, we can see that it gives a weird number. This is the memory address the y is actually stored in. By itself, this is a normal integer actually. Like there's nothing special about it on the hardware level. This is just an integer that stores the value of 0x15. And by itself, this will be extremely useless. But what we can do is we can dereference the integer and access the memory slot that's stored in 0x15. So if we just say x equals 20, this would actually crash because, as I said, x is not a normal variable, but it points somewhere in this memory. These are the 0x13, 0x14. So if we just assign a normal variable, normal number, it won't work. We need to assign a specific, we need to assign its memory address value. But what can we do with this address? Is that we can dereference it, as I just said. If you put the star sign before the x, and then you make it equal to, let's say, 30, what this will do is it will check, instead of assigning it to x, it will check the value that x is pointing to. In this case, it will be 0x15, and it will go to the memory slot and it will overwrite this memory here. So instead of the value x being 30, if the memory address at 0x15 will become 30. So let's try that. So as dereference x with a pointer with a star symbol, let's make it 30, and let's print y. We are not going to print x because x is pointing to the memory address that stores the variable y. So if we dereference x and assign 30, we are overriding the memory address that stores the value y. In fact, let's print the y first here, and then we can print it again after assigning it. My bad. So as you can see, at first it is just a normal variable, and then we assign x to the memory slot, it is stored at, and then we dereference it, meaning we want to write to x, but we will write to the address that x points to, and then we will overwrite that address with 30, and then we will print y again. In this case, it becomes 30. Now, what we can do with this information? There's many useful things. One of the most basic examples is you can pass memory addresses through function calls and then modify the original variable. So imagine we have a function called multiply with 2 that takes an integer x and then it returns the triple of the double of that. So we have a variable 10 that we want to get the double of. What we can do is we can create a new temporary variable and then call this function, and then we can print it like this. So this will print 20. Now, if we try to do something like this, but instead of returning it, we just try to do this will not work. And let's just delete it. Call it like this. This will not work because parameters, they get their own copies. Instead of modifying the original variable, the compiler creates new copies for each parameter. But let's say in this function, we want to modify the actual value of a. To do that, we need to pass the memory address that a is located at. So we can just put this here. But if we try to run by itself, this will not work because now this is the memory address of a, but the compiler, the function, expects a normal variable. We need to let it know that the value the parameter holds is not a normal variable, but it is a memory address location. So to do that, we just need to turn it into a pointer. So now the function expects the variable x to be not a normal number, but a memory address. And then if you just try to run like this, again, it will not function because now we are trying to change the memory address. I mean, this is supposed to be this way. We are trying to change the memory address. But what we want is we need to change the number that is stored inside that memory address. So to do that, we can simply dereference x and then multiply it by 2. And if we just run it, as you can see, it doubles the a. It doubles the value a. Now, what is going on in this call is that it might look complicated, but do not worry. So let's analyze it from the ground up. So we have a variable a. There's nothing fancy about this. It is just a variable. And we have a function called m_t that expects a memory address. It doesn't expect a normal variable, but a memory address to a variable. So we call this function not with the normal value of a, but the memory address that a is stored at. So if a is stored at, let's say, memory address 0x15, this becomes 0x15. And what we are doing here is that instead of changing the memory address itself, we look at the value that is stored inside the memory address. So if x is, let's say, 0x15, we are looking at the value that is inside the memory address 0x15, and then we are multiplying it by 2, and then we are just printing it. And yeah, in the next video I will take a look into different types of pointers. For example, it doesn't have to be an integer. You can have a char pointer, an unsigned int pointer, and they have differences. I will get into them in the next video. And then I will also get into memory allocating and freeing and like reallocating in the standard library. Thank you for watching.